Good morning friends. In today's video we are going to see the design of duct system which is used in different applications like FAHU supply and return ducts, fan coil unit ducts, toilet ventilation, staircase pressurization, like that. So when you see different design drawing and design report, you might have noticed that the designer can use different equal friction value in the equal friction method like 0.08 inch per 100 feet, 0.1 inch per 100 feet, and similarly for the constant velocity method they will use 5 meter per second, 4 meter per second, different values. So we need to know what exactly ASHRAE and SMACNA standard limitation and its requirement. So let's start the video. So you can see this graph which I have taken from SMACNA Duct Design. You can see the similar graph in the ASHRAE Application Handbook also. So in this graph, if you see here in the X direction, they have given the air quantity in CFM. The unit is CFM. In the Y direction, it is given in the friction. They have given the friction loss. The unit is inch of water column per 100 feet. Okay, and similarly you can see in this sliding line 300, 400, 500 they have given the velocity value and also the duct diameter in I mean the circle diameter they have given, like you see here 3 inch, 4 inch, 5 inch, 6 inch, 7 inch, 8 inch. So these are the value we have given in the graph. So when we go for the duct design, we have to make sure that our duct design selected values are falling in this gray area, gray shaded area. So for example, in the equal friction method, if you are using, then the equal friction value will be, you can see this value 0.08 from this shaded area where it is starting, from where it ends 0.6 inch of water column. So our value between 0.08 to 0.6 inch should be there. And you can see the graph, it is continuing like this, and up to some point it is going down like this. So here you can see the maximum velocity. This is the velocity. It is 4000 feet per minute they have given. The concept here is you can see the airflow 10,000 and here it is 20,000. That means around 16,000. So till 16,000 CFM you can use this concept, and when the airflow is going more than that, you have to make sure that the velocity is not exceeding 4,000 feet per minute. For example, if you say your in your project the flow is 10,000 means you can see the 10,000 is here. That means you can follow, if you are using equal friction method, you can follow the equal friction between 0.08 to 6 inch. Suppose in your project the flow is 25,000, that means it is more than this arrow. So here it is somewhere 25,000. So for the 25,000 means you have to make sure that the velocity is not exceeding 4,000 feet per minute. So I will show you one example so you can understand it very easily. So what you see here is the fresh air handling unit, and from the fresh air handling unit we have the supply side, the blue line, and the green line you can see the return one. So first if you see the supply line which is supplying to different floors like this, so there are different flow supply connection is there, and if I see any one flow like you see here, this supply connection 226 liter per second which is going to supply different fan coil unit because this is the fresh air requirement. Now I will take this value 2903 liter per second, which is the air coming from the fresh air handling unit. Now I will go to the duct sizer. So you can see here the duct sizer, and the flow value is 2903 liter per second. But before that we have to correct one more thing. You can see the arrangement like the air temperature. So there will be different temperature limit will come. So 30 degrees Celsius, 97 RH and this thing. So we will normally make 50% RH and 1 atm and 25 degrees Celsius for the design. So after making this one, you can see the flow rate 2903 liter per second. Let me convert this one to CFM, 6151 CFM, and the head loss as I told you in the shaded area like you see here, we can make from 0.08 to 0.6 inch of 100 feet. So that is what I am going to follow here. I am going to follow the minimum value 0.08 inch per 100 feet, and the velocity it will automatically come, and the equivalent diameter for the circle duct it is given here. Now for the rectangle duct I need to decide. So for example, if you see this site, for example this is the site condition, this is the top view, this is the top view of the site in the roof. So here we have, for example, we have one FAHU here, one FAHU here, and this is the duct, yellow colorish duct, and this is a shaft which is going down. The duct is going down, and there are different outdoor units are located here. So normally the roof we will get some most of the project we will get very limited space to pass the duct because the exhaust fan, fresh air, FAHU, AHU, FCU, I mean so different unit will be located. So that is the reason we have to see the site condition. What is the width of the duct I can make. Whether I have no limitation mean I can increase the width. Otherwise, I have to see what is the acceptable width in the site. That is the first case. Second thing, the aspect ratio. So aspect ratio is another important thing. For example, here I will put the duct size. For example, 32 inch I am adding here. So if I put 32 inch, either it can be weight, it can be width or height, whatever. That is not an issue. You will get another size. So 32 inch. So the aspect ratio means, so like many people say aspect ratio means is width by height. No, aspect ratio means the higher side by lower side. Okay, so the higher side means here you can see a higher side is 32 inch divided by the lower side is 22 inch. So the aspect ratio is 1.45. So normally you see the aspect ratio as per SMACNA and ASHRAE Application Handbook, they are recommending the aspect ratio should be close to 1. That is a very perfect design, but it must not exceed 4. The aspect ratio must not exceed 4. So here in our case the aspect ratio is 1.45, that is the acceptable limit. So similarly you can change to any size. For example, if I put 40 inch, I am saying that in my site maximum width I can go, but height I cannot go in the site condition. So if I put 40 inch, so this value is coming 18 inch the height. So that time you can see what is the aspect ratio, 40 divided by 18. It is 2.22, so it is still acceptable. We must not exceed 4. We try to maintain near to 1. So as I told, you can adjust the duct height and width based on site condition. For time being, I consider 32 inch. That is not an issue. 32 by 22 inch. That's the duct size. So I will convert this one to mm. So 32 means, so you can multiply with 25. It is 800 mm. And 22 means 22 into 25. It is 550 mm. So the duct size here is 800 by 550 mm. So this is how we will find out the duct size. And going with the next one, which is going inside the room. Okay, so it is 226 liter per second. So if you can make the same arrangement here, you can go to this one, you can say like 226 liter per second, and I am going to follow the head loss like 0.08 inch per 100 feet. So similarly you can adjust the duct size. For example, 10 inch if I put 10 by 10, otherwise if you put 12 inch, so it will become 12 by 9 inch means you should not always put the 9 7 like that. You have to make to the next round of value, that is a 10 inch. Okay, because rectangular duct we always fabricate like that only. So here it will be 12 inch by 10 inch. But the important problem with this arrangement is, nowadays most of the client, they want the noise level is very limited value for each and every design. For example, if you see the ASHRAE Application Handbook also, they have given the noise value for the different application. Like you see here the residence area, they have given 30 RC or NC, and similarly if you see here, like if you see here the meeting room, they have given 25 to 35, corridor lobbies 35 to 45, telephone room 25 maximum. So these are the important thing they have given in the ASHRAE Application Handbook, and most of the client want we to follow this one in our design. So that is the reason I would recommend you to follow this one also. That is I have taken from ASHRAE Application Handbook. So because in the last model what we saw in the graph, there is no value for the noise level to limit the noise level. That is they have given the velocity that is acceptable, but most of the project, as I told you, the client want to follow the noise level, limited noise level. For example, like you see here in soft area means like you see here the design. So these are the soft area which is going down, soft area, and after that we have the tapping area means this FCUs are located inside the room. So this is the tapping area inside the room. And second thing, this one you see above suspended acoustic ceiling. Suppose in your project the ceiling is acoustic value, so because of the project requirement, then you have to follow this arrangement. Suppose in your the third one is duct located within occupied space. So for example, you have a office room, so office room and you are sitting there, so the duct is located above your head, like in the ceiling area. So that time you have to follow this requirement. So there are 3 requirements are there. We will see how to design based on this one. So first in this video I will tell you all the available methods, and finally I am going to explain what based on my experience how I am doing the design throughout my life. Okay, so all these things I can explain, so you can see, you can compare the design. So here I have shown one snapshot from my recent project. So here you can see different rooms like lobby is here, and here you see the reception and store room, utility room, and different arrangements are there. So we will consider, for example, we will consider one duct system, this FCU supply. Then we will see how the values are coming. First, this lobby, we don't have any acoustic requirement, and below this lobby, you know that the people will be moving here and there. So this you can see the three category. It will not fall inside the soft area. It will not fall in the category of above suspended acoustic ceiling, and the third category, duct located within occupied space. So the FCUs in the ceiling area, inside the ceiling. So I can use the third category because there is no acoustic ceiling requirement in my project, and it is not in the soft area also duct. So for this one I am going to follow this requirement, and you can see this is the lobby area. First we will go to ASHRAE Application Handbook. You can see for the lobby what is the maximum noise level we need to follow. So the corridor and lobby they have given 35 to 45 based on the ASHRAE Application Handbook, and I am going to follow this value. I'll consider the minimum value 35 for the safe design. And for the 35, you can see the maximum NC or RC 35 means your duct velocity must not exceed 1450 for the rectangle duct, and for the round duct it should be maximum 2600. So you can see the airflow value for this FCU. It is 431 liter per second, which comes from cooling load calculation. And you know the maximum velocity for in our case, it must not exceed 1450. So using these two conditions, let me design the duct design. First thing, you can see the flow rate. It is 431 liter per second is equal to 913 CFM. So I am going to apply the same value here, 913 CFM. And what is the maximum velocity we have from the ASHRAE Application Handbook? It should not exceed, it must not exceed 1450. Okay, and you can see what is the head loss you are getting by using the ASHRAE Application Handbook maximum velocity and your accurate airflow. You can see the value is 0.304. That means your head loss for the full FCU duct, I mean the balance branch duct also, it must not exceed 0.304. Now I will go back to the shaded area. So now you will be clear. You can see 0.3 is 0. This is 0.2. 0.3 is somewhere here. So this is again in between the shaded area. As I told you earlier, you can follow the friction loss from 0.08 to 0.6, and now you got the value of 0.3. So which is still acceptable, and you are complying to the noise level, you are complying to the velocity. So you are complying to overall. So here based on the maximum velocity, the maximum head loss is 0.304. But it is not a rule that I have to follow exactly 0.3, but I need to follow less than 0.3, and I have the tolerance. Now based on this chart, I have the tolerance from 0.08 to now 0.3. Then we can comply the acoustic requirement. So for in this example, as per that chart, 0.3 I need to use for all the duct sizes. But this is the one case. So now I'm going to explain you what I am following in my design, and based on that we will see in this video we will see how to we'll decide. I'll show you some design for the soft riser, and inside it design the pressurization fan, all the thing one by one I'll show you based on my recommendation, which I am following by complying with the ASHRAE Application Handbook and SMACNA Duct Design. So first thing, for the FAHU fresh air handling unit, whether it is a roof duct or riser duct, I am following 0.9 Pascal per minute or per meter, or 0.1 inch per 100 feet. So when I following this one means I will also check this value also. When I use that value, I will check the maximum velocity. I will consider the maximum velocity also. So then let's see what the answer comes using this method. So first the roof and riser duct, 0.9 Pascal or 0.1 inch per 100 feet, and tapping from riser duct. Tapping from riser duct means which is falling inside the room, supplying inside the room. You can see here this duct is supplying inside the room now, this one. So this one I have to follow that value 0.7 Pascal per minute or 0.08 inch per 100 feet. So let's see first the design. So first for the FAHU is 2903 liter per second. So let me go to the duct sizer. 29 before that I will set this one, okay, 25 degrees Celsius. So 2903 liter per second, and the head loss as per my data here, you can see 0.9 Pascal per minute. So I'll follow the same one, 0.9 Pascal, and you can see the maximum velocity 7.8. So this one, as I told you, I must verify this value with the ASHRAE Application Handbook or the project requirement. So which is equal to 1536 feet per minute. I just convert this one to SI and metric unit change. So 1536, I will go to the ASHRAE Application Handbook value, and this arrangement will come under in soft because we are doing for the roof now, roof duct. So here there are different NC values are given. Of course, in the roof we can go with a slightly higher NC value. For example, you consider that for 45 or 35, any value based on your project requirement. So let me consider like 35 for example, and 35 NC value, the velocity must not exceed 2500. This is the first thing I have to verify. So in my case the velocity is only 1539, so I am in the very safe limit of the design, and the design is acceptable. So as I told you, I am going to use 0.9 Pascal, 0.9 Pascal per minute, and here the arrangement is duct size I can adjust based on the aspect ratio. For example, if I put 800 by 500, suppose in your site you have the limitation for the height, you cannot go more than 600 mm. So for the height, okay, maximum 600 means the width you can go with it 650. So the aspect ratio, if you check 650 by 600, it is a very good, like 1.08, so very near to 1, so it is acceptable. So the first duct design I can use 600 by 650 for the this duct, 600 by 650. And coming down the riser, the first tape, the taping off, you can see the taping point which is going to supply to the different room. It is 303 liter per second. So coming back to my data here, so tapping from riser duct you can use slightly lower, okay, because this is going inside the room now, so we don't need to go with a higher value of 0.9 or 0.1 inch. So sometimes the project the people are following the same for the inside the tapping also, but I would recommend to go slightly lower because the noise will be the issue. So that time, okay, 0.7 Pascal or 0.08 inch, so it is still acceptable in our chart which I showed you earlier. So if you see with this one 0.08 inch, and I'll go to the design, 303 liter per second, you can see it is 303 liter per second, and the duct head loss is, as I told you, 0.7 or 0.08 inch per 100 feet. And the duct size I will convert, make to other one, 300 by 300, or you can go with 400 by 200. This is as per your wish based on the site condition, and how to make sure the aspect ratio is falling within the limit. So I will follow the duct design here, 400 by 200 what I got from our duct design. by 200. So coming to the next step now, after this tape up, you can see it is 77 liter per second, because we have another branch which is going to the left side of the room, so other values are there. So let me do the same thing for 77 liter per second also. So 77 liter per second, the same head loss 0.7 I consider, and I can change the duct size. If I say 250 means it will be 150, 250, 125 means 125 is not acceptable as what I told you, so it will be 150. So if I make 200, 200 by 150, so you can make based on site condition. So the second one will be 200 by 150. So this is how you have to do the duct design for the FAHU soft riser, roof duct, and also the inside tapping point. I'll show you one more thing also, 2600. So 2600, as I told you, for the this is the riser, this is not the, this point is the riser point, this is not the branch into the room. So that's why I told you I'm going to follow the next one, the first one, 0.9 Pascal. So if you follow 0.9 Pascal here, 0.9 Pascal, and it will be, you can adjust the duct size. For example, if I make 400 by 950, or if I make 800 by 500, so different duct size you can arrange. So this is how we will follow we'll do the duct design for the FAHU, considering the roof and riser one velocity, one friction loss, and inside of the duct one friction loss. And the next one is the FCU supply duct, return duct, whatever it is. So you can follow 0.6 Pascal per minute or 0.07 inch per 100 feet. So if you, when you go for the design, you have to verify the velocity also within the limit. Let's see one example here. So for example, in my design, the last project which I did, you can see 431 liter per second, which is the lobby area. So lobby area, now here there is no requirement for the noise level. So I'll follow 35 as per the ASHRAE Application Handbook. So as I showed you, ASHRAE Application Handbook, 35 to 45 is acceptable. So I'll go with the 35. So 35 means maximum velocity must be within 1450. So let me take my data, then let's verify the value. So here you see 0.6 Pascal per minute is the value I'm going to follow for the design now. In In this project, you can see the airflow from the cooling load calculation is 431 liter per second. I'm going to apply the same value, 431 liter per second. So as I told you, the head loss for the inside the supply duct for the FCU or supply and return, you can follow 0.6 Pascal per meter, and the velocity value 4.178. You must verify the velocity value. So if I convert this one to feet per minute, it will be 824 feet per minute. And if you see the ASHRAE application handbook for the 35, I told you to consider, because we don't have any acoustic requirement. The velocity must not exceed 1450 feet per minute. So in our case, we have 824 only, so it is still in the acceptable limit. We can follow this duct design. Now coming to the sizing, in this design, if you see here, it is 450 by 250. And if you make for example 450, because here there was some height requirement in the ceiling void, so 455 follow, it is 250, the same answer what you see here, 450 by 250. So similar to this one, I can show you other example also. For example, this stage it is 323 liter per second. So the same concept, 323 liter per second. I'm going to follow the same head loss, 0.6 Pascal per meter, and the duct size, if I make 450, it is 200. So you can see the same duct size, 450 by 200. And the next one, for example, to one branch duct, for example here 108 liter per second. You can go with the 108 liter per second, the same head loss, and the duct size, if I change for example 300, it is 125. As I told you, 125 is not acceptable in the duct design. We have to go to the next round of value, that is 150. So the duct size is 300 by 150. So now you are clear with the FCU supply duct. Same you can design for the return duct also, and FAHU already told you. And now we will discuss about the ventilation and the smoke pressurization. And in this video, you can in this drawing you can see we have the PF, the pressurization fan, which is supplying to the staircase. So like you see here, the main soft duct is there, and which is passing to different levels. Like you see here, 1550 liter per second, which is passing at a different level. And similarly, I can show you one ventilation soft exhaust fan, which is located in the roof also. And here from each toilet, for example, one water closet, 125 liter per second they have considered. So this exhaust fan located in the particular side of the shaft, which is taking this toilet exhaust 25 liter per second. And similarly, if you go to different levels, it is considered like 25 liter per second, and then further it is adding 25, 50 liter per second, then 75. So like that it is going there. So we will see how to make the duct sizing for these two also now. So for the pressurization duct first, so the roof and soft duct, you can follow the equal friction value of 0.9 Pascal per minute as 0.1 inch per 100 feet. Since the noise is not an issue in the roof and soft, slightly you can increase the value based on the site requirement, but I would recommend go with 0.9 Pascal per minute, similar to our FAHU, the soft and roof duct what we did. For example, in our project, if you see here, the first value what we see here from the fan, 9300 liter per second is coming, which is going to the shaft here. So we'll go to the duct sizer, 9300 liter per second, and the Pascal, as I told you, maximum 0.9 Pascal. And the duct size you can adjust based on the shaft requirement. For example, 1000 by 950 or 1200 by 800. So this one you can adjust in the site. As I told you, 0.9 Pascal you can follow, but sometimes the noise is not a concern for that location. So slightly the values are there, we can increase, like 1.2 also we can go. But I would recommend to go with the 0.9, that's not an issue. And the next important thing is the supply duct, which is passing to this grill. So this supply duct, most of the code, for example, if you see this UAE's life and safety code, for the staircase pressurization, they will say that the supply air velocity must be 5 meter per second maximum. Similarly, if you go to Qatar, they have the maximum supply air velocity to the last 10 minutes. So that is the reason I will follow that the value. So the velocity must not exceed 5 meter per second. So I would go. I will recommend you to go with the 0.4 Pascal per minute for the last end point. For example, if you see here, 1550 liter per second for the supply area. So if you see here 1550, and as I told you, the head loss I will follow 0.4 because the velocity I want to limit to 5 meter per second. So in this case, if you change it, you can adjust the duct size for making the aspect ratio close to 1 if possible. So here 800 means 425, 425 means 450. So 800 by 450 is the duct size for this arrangement, and I am complying the velocity, maximum velocity limit also. So similarly, if you go down, you can see the next value. One more thing I'll show you, 7750, which is located in the shaft. So 7750, if it is in the shaft, then we can follow 0.9 Pascal. and the duct size you can adjust based on the site requirement, whatever the value. And second thing, for the branch it is 1550, it is constant value for the all the branches 1550 I am following, because equally we are distributing the flow. So the same you can follow with the 0.4 Pascal, and the velocity must be based on your local code requirement. So this is how we can design for the staircase pressurization duct. So going to the next one, we have the ventilation. So for the coming to the ventilation duct, for example toilet ventilation, kitchen exhaust ventilation, you can follow the value of 0.9 Pascal per minute or 0.1 inch per 100 feet. And coming to the car parking, because here I am telling to value follow this one. For example toilets are located inside the building, and so that's why the maximum value what we follow for the FAHU riser and the shaft one, we can follow the same value 0.9 Pascal or 100 feet or 0.1 inch per 100 feet. Coming to the car parking is the area where the noise is not that much is concerned. So you can slightly go with a higher value like 1.2 Pascal per minute. You can go for the car parking ventilation, and also car parking that area, car parking area, as well as the shaft area, as well as the roof area, together you can follow 1.2 Pascal per minute. And coming to toilet and kitchen, 0.9 Pascal you can follow throughout the area. For example, you will see in our design. So here if you see here, to this point, for let's say for the example 125 liter per second. So I'll make the value 125 liter per second. Let me change this one first. 125 liter per second, and the head loss, as I told you here, 0.9 Pascal per minute. You can go with the 0.9 Pascal per minute. So velocity is low. The duct size you can make, for example 400 means 400 by 100, or you can make 200 by 200. So different duct size you can follow. So 0.9 Pascal per minute you can consider for the ventilation duct, the toilet ventilation. Otherwise you can say the kitchen exhaust, all this one. For the car parking you can go with this slightly higher 1.2 Pascal per minute. So like this you can do the design for any duct considering this this value, whether it is the soft duct or roof duct or the inside the tapping duct, for the ventilation staircase, for all this arrangement. But as I told you, once you you can follow this value which is falling which is complained to ASHRAE Application Handbook and SMACNA, the shared area requirement, and you have to verify the thing like the maximum NC value is within the limit. Okay, because sometimes the client will give the project requirement NC, so you have to comply to that requirement. So this is the way you can do all the duct design. So thank you for watching the video. So if you have any doubt, please add your comment in the comment section. I'm happy to serve you. Thank you. Bye bye.